Affordable telescopes like the Dwarf II Smart Telescope from Dwarflab or the Seestar S50 from ZWO are becoming more and more popular nowadays. Both of these telescopes are available for around $500, and I already did some separate review videos on both these telescopes, so if you're interested you can find some links in the video description below. But in this video I'm going to do a direct comparison between the Dwarf II and the Seestar S50. So we're going to capture the sun, we're going to capture the moon and some interesting deep sky objects using these two telescopes. Let's go!
The Dwarf II is currently priced at around $419 or euros and includes a bag, a small tripod, a 64GB micro SD card and battery. There is also a deluxe version available for $539 or euros, which comes with an extra battery and additional solar and astrophotography filters. For a 5% discount on the Dwarf II, you can find a link in the video description below. At the time of this video, the Seestar S50 Smart Telescope is priced at $499 or euros and includes a small tripod, a sturdy case for storage, a USB-C cable, a solar filter and a built-in duo-band light pollution filter. This telescope also comes with a 54GB internal eMMC storage card. You'll find links in the video description below to purchase the Seestar S50 directly from ZWO or from reliable telescope retailers in the USA and Europe. At this moment in time, European retailers are selling this telescope for an astonishing 700 to 800 euros, which seems quite unreasonable. However, if you're open to purchasing directly from ZWO, you can follow the link provided in the video description below and buy the telescope for $499. Despite being labeled as a smart telescope, the Dwarf II actually uses a telephoto and a wide-angle lens. Its telephoto lens boasts 8 megapixels with a 24mm aperture and a focal length of 100mm, resulting in an f-ratio of 4.2. This telephoto lens is paired with the Sony IMX415 Starfish sensor featuring remarkably small pixels measuring just 1.45 micrometers. This configuration provides a 2.7 by 2 degree view of the night sky, delivering a resolution of 3 arcseconds per pixel. To put that in perspective, the camera's field of view covers approximately 5 times the moon's diameter in width, with the moon's diameter spanning about 600 pixels. The second wide-angle lens on the Dwarf II is a 2 megapixel lens with a 20mm aperture and a 48mm focal length. The wide-angle lens provides a generous 50-degree field of view. While not designed for photography, it serves a valuable purpose in locating and framing objects within the view of the telephoto lens. The Dwarf II telescope takes photos in JPEG as well as higher quality TIFF and FITS formats when in astro mode. Videos are recorded in MP4 format in HD. Unlike a traditional lens, the Seestar S50 features a genuine triplet aphochromatic refractor telescope with a 50mm aperture and a 250mm focal length, resulting in an f-ratio of f5. It is equipped with an integrated 2 megapixel Sony IMX462 camera sensor boasting a 2.9 micrometer pixel size. The Seestar provides a viewing angle of 0.7 by 1.3 degrees with a pixel size of 2.39 arcseconds per pixel. To put it in perspective, you can comfortably fit the full moon in that field of view, with the moon's diameter spanning about 753 pixels. The Seestar S50 offers a narrower field of view than the Dwarf II. However, the moon will appear approximately 25% larger when observed through the Seestar S50 as compared to the Dwarf II. The telescope supports capturing pictures in JPEG and FITS formats, as well as recording videos in MP4 and AVI RAW formats. Additionally, both models can be controlled through apps on your smartphone or tablet, compatible with both iOS and Android devices. Lastly, both telescopes feature a computerized altitude azimuth mount for locating and tracking celestial objects in the night sky.
Okay, let's start by capturing the sun. And remember, never look directly into the sun with the naked eye and always use the dedicated solar filters that come with each of these telescopes. So Let me show you how that works.
Let's begin by showing you how I captured the sun with the Dwarf II telescope. The Deluxe package includes 2 solar ND filters which can be attached to the adapter and placed in front of the telescope's 2 lenses. To start, power up the telescope and connect it to the Dwarflab app you can download on your smartphone or tablet. The app prompts you to establish a Bluetooth connection with the camera. Once connected, you'll need to switch to the Dwarf II Wi-Fi signal and click on the photo button in the app to begin. The app interface displays the telezoom lens view with a window in the top left corner showing the view of the wide-angle lens. You can easily switch between the 2 views by tapping on the window that shows the view of the other lens. To adjust the telescope's direction, use the button located at the bottom left. Dragging it enables movement and 4 arrow keys representing different directions become visible. On the bottom right, there's a track icon that, when pressed, reveals a vertical slider controlling the telescope's slew speed. You can adjust the slider to control how fast the telescope moves. In the wide field view, a green rectangle indicates the telezoom lens's field of view. Once the sun falls within this rectangle, you can switch from the wide-angle lens view to the telephoto lens view. I find this method of locating objects where the wide-field lens acts as a finder scope incredibly convenient. You can fine-tune the lens settings by selecting the settings icon located on the left beneath the switch screen icon. Within the settings menu, you have the option to adjust exposure time, gain, white balance and decide whether or not to use an IR cut filter. Removing the IR cut filter proves particularly valuable for capturing images of deep sky objects, and we'll explore that later in the context of deep sky imaging. Dwarflab suggests setting the shutter time to around 1/200th of a second with the gain set to 0 to capture the sun. It's worth noting that you can zoom in on the object you're focusing on by pinching your screen. To achieve precise focus on the sun, click on the focus icon situated on the right. The autofocus option didn't achieve optimal focus for me, and I found using the up and down buttons to achieve focus manually more effective. I focused carefully on a few visible sunspots that day, and once focusing is complete, you can click on the feature that displays Sun in the top right corner of the screen. By selecting the Sun option, the app prompts you to ensure the Dwarf II telescope is placed on a flat surface and equipped with the ND solar filters. After confirming these requirements, the Smart Telescope initiates tracking the Sun, keeping it centered in the sky. After that, you can easily choose the video mode and hit the record button, triggering a timer displayed on the screen. I captured a few 1-minute videos of the sun. In photo mode, you can capture a snapshot of the sun simply by pressing the shoot button located on the right side of the screen. All photos and videos are stored on the micro SD card and in the album of the Dwarf II telescope app. I also captured the sun using the Seestar S50 Smart Telescope. The telescope can be controlled by downloading and installing the Seestar app, available for both iOS and Android devices. In the video description below, you'll find a link to another video explaining in detail how I installed the Seestar S50 app for the first time. Once you open the Seestar app, you'll need to connect to the Wi-Fi signal of the Seestar S50 to gain control of the telescope. The start screen of the app displays relevant information for aspiring astronomers, such as the rise and set times of the sun and the moon, details about deep sky objects you might want to explore, and more. Additionally, you'll find different telescope modes: stargazing, solar, lunar, and scenery. When selecting solar mode, the Seestar app prompts you to place the solar filter in front of the telescope. On the right side of the picture, there are up and down arrows that allow you to move the telescope up and install the filter. Once the filter is properly installed, you can press the Install and Shooting button. The Seestar S50 will automatically search for the sun in the daytime sky and center it within the telescope's field of view. This automatic centering mode is generally effective, although it may occasionally encounter difficulties. In such cases, you can either return to the main screen and restart the process, or manually adjust the direction of the telescope to view the sun. To manually align the telescope with the sun, press the gray circle in the middle of the screen and utilize the slew buttons to center the sun in the telescope's field of view. I find that using the slewing buttons on the Seestar S50 can be a bit more challenging compared to adjusting the Dwarf II. When you drag your fingers further outwards, the slew speed of the Seestar S50 increases and you simultaneously control the direction in which the telescope moves. This can be a bit trickier than the Dwarflab app, which employs a separate slider to set the slew speed. Alternatively, you can also swipe the screen on your phone to make subtle adjustments to the telescope's position and precisely center objects like the sun. Once the sun is centered, the Seestar S50 will automatically start tracking the sun to ensure it remains within the telescope's field of view. The default camera settings of the Seestar S50 are highly effective, eliminating the need to manually adjust the exposure time, gain, and white balance as is required with the Dwarf II. Autofocus can be activated by pressing the autofocus icon and positioning a green rectangle on the area that requires focusing. The autofocus feature worked really well. At the default settings, the celestial objects consistently appeared sharp and well illuminated in the telescope's view. You have the flexibility to capture the sun in different video formats. Standard videos are stored in MP4 format on your smartphone. Alternatively, you can record high-quality videos by selecting RAW. The videos are stored on the telescope's eMMC storage card in a folder called My Works. MP4 videos typically take up approximately 70 megabytes per minute, while RAW videos take up about 1.4 gigabytes. RAW videos are much higher quality videos, averaging around 12 frames per second. They can be further processed using dedicated Astro tools like AutoStacker or Registax. In addition to videos, you can also capture snapshots of the sun in JPEG format by choosing the photo option at the bottom of the screen. The latest version of the Seestar app also includes a time-lapse feature for the sun, allowing you to select intervals for tracking the sun. There's also a time-lapse option on the Dwarf II Smart Telescope. Let's do a direct comparison between the videos and processed images of the sun captured with the Dwarf II and the Seestar S50 Smart Telescopes. Seestar S50 offers a higher quality recording format in AVI RAW and boasts a 25% higher resolution of the sun as compared to the Dwarf II. Obviously, the Dwarf II captures the sun in its natural white color, while the Seestar S50 captures the sun in a nice orange glow. When zooming in, the superior resolution and quality of the Seestar S50 are clearly evident, at least in my opinion. Nevertheless, the broader field of view offered by the Dwarf II could be advantageous for capturing scenes like a beautiful sunrise or a sunset in scenic spots. The Seestar's narrower portrait view limits its ability to capture such panoramic views.
Alright, so let's wait until nightfall to capture the moon and some interesting deep sky objects with these two smart telescopes.
It was easy to point the telezoom lens of the Dwarf II at the moon in the app using the wide-angle lens view. I adjusted the telezoom lens settings to the same settings as used for viewing the sun, being 1/200th of a second exposure at 0 gain. I zoomed in on the moon by pinching my smartphone screen. Upon switching to the telezoom lens, I tested the autofocus feature, but it didn't perform well. I manually focused the lens on the moon using the plus and minus buttons. Following this, I attempted to use the sun's tracking feature in video mode to track the moon, considering the sun's similar movement across the sky. However, it failed as it's exclusively designed for solar tracking. I chose to focus on the moon and capture a few 1-minute videos without tracking and noticed a subtle movement of the moon within the camera frame. At present, the Dwarflab app only records videos in MP4 format. You can also use the Astro mode to calibrate the telescope and use the automated go-to function to track the moon, which I'll demonstrate in a minute. Using Astro mode is quite challenging in my opinion, so I decided to take a 1-minute video of the moon instead. Let me also show how I captured the moon using the Seestar S50, and let's compare the results. Within the Seestar S50 app, I selected lunar mode and the telescope automatically flew to the moon, centering it in the field of view. Once again, the default settings proved to be excellent, presenting a sharp and bright view of the moon through the telescope without any need for adjustments. Just to confirm, I utilized the autofocus option, which worked really well, rendering a crisp view of the moon's craters. I opted to record some 1-minute videos both in MP4 and AVI RAW format. Here's a comparison between the videos and pictures of the moon taken with both telescopes. On the right, we can see the videos of the Seestar S50 with the lunar craters and mare sharp into focus when looking at both MP4 and AVI RAW video formats. Despite my best attempts to focus on the moon with the Dwarf II, the zoomed-in MP4 video didn't achieve the same amount of detail as compared to the Seestar S50. This difference between the two telescopes also showed in the single JPEG pictures as well as the processed stacked pictures. If you'd ask me why this is the case, I'd say there are a couple of reasons. For example, the aperture of the Seestar S50 is twice the size of the telephoto lens of the Dwarf II and the focal length is about 2.5 times longer. This really helps to get a higher resolution picture of objects in space. Also, the Seestar S50 is a dedicated telescope with high-quality lens elements, whereas the Dwarf II is a telephoto lens, which is developed to function as an all-round camera instead of a telescope that is specifically developed for crisp night sky imaging. However, as mentioned earlier, I do appreciate the wide-field perspective offered by the Dwarf II, making it suitable for capturing the moon in scenic landscapes. I also tested the Dwarf II and the Seestar S50 on two deep sky objects, being the Andromeda Galaxy and the Eastern Veil Nebula. Both telescopes track the night sky in altitude azimuth mode instead of equatorial mode, so the maximum exposure time for individual deep sky photos are limited. The Seestar is automatically limited to 10 seconds, whereas the maximum exposure time is limited to 15 seconds for the telezoom lens of the Dwarf II. This technique is called lucky imaging, and it's an affordable way of doing astrophotography where you stack many 10 to 15 second photos together with the aim to increase the signal to noise ratio of a deep sky object. The Andromeda Galaxy is an awesome deep sky object that should be on every backyard astronomer's checklist. It is our closest neighboring spiral galaxy and it appears as one of the biggest objects in our night sky. Although the Andromeda Galaxy is a whopping 2.5 million light-years from Earth, it's over 220,000 light-years in diameter and home to 1 trillion stars. Due to its immense size, it shows up in our nighttime sky as 6 times the diameter of our moon, making it extremely captivating to photograph. Since the Andromeda Galaxy emits light across the entire visible and infrared spectrum, it's recommended to capture it without any astrophotography filters in areas with minimal light pollution. I've personally photographed it without using any light pollution filter using the Dwarf II and the Seestar S50 in an urban environment. Keep in mind that capturing this incredible object under darker skies will likely result in even better pictures than what I'm about to show you. I pointed both telescopes at the Andromeda Galaxy during the same night, taking 10-second photos for about 50 minutes. Let's begin with the Andromeda Galaxy and the Dwarf II. Before starting capturing deep sky objects with the Dwarf II telescope, it's recommended to create a dark library using Astrodark mode in the Dwarflab app. For detailed instructions on how to do this, check out the link to a tutorial in the video description below. Once you've selected Astro mode in the Dwarflab app, the first step is to calibrate the telescope to determine its position in the night sky. Ensure you have a clear view of the night sky and the telescope should be in its initial position with the lens turned approximately 45 to 80 degrees up. Focus the telelens on a bright star visible to the naked eye. Achieve a good focus on these stars with a shutter time of about 1 to 2 seconds and a gain of around 80. After successfully focusing on a star field, hit calibration in astro mode. The telescope will move up and down and perform about 3 calculations and then display calibration success. Following this, you can select features and choose Auto Go To, which presents a list of famous deep sky objects. Select M31, the Andromeda Galaxy, and the Dwarf II will automatically slew to the chosen object in the night sky and initiate tracking. Once tracking is underway, increase your shutter time. For photographing the Andromeda Galaxy, I recommend using approximately 10-second exposures at a gain of 80, a white balance of 4000, and with infrared pass turned on. After that's done, it's always a good idea to recheck your focus on the stars. When the stars are in focus, you can select features and click on More. This will bring up a menu where you can input the number of pictures you want to take. I opted for about 250 pictures in FITS format with the display stacked. Stacking the pictures allows you to see how each picture contributes to the previous one, enhancing the signal to noise ratio with each new photo. In capture mode, you can exit the app and the Dwarf II will continue capturing the object. You can reconnect with the Wi-Fi signal and the app at any time. I must admit that I find the numerous steps involved in capturing deep sky objects a bit daunting. Additionally, calibrating this telescope was a bit of a hit and miss. There were instances where the calibration failed and I received a failed to get the motor position message, requiring me to redo the whole calibration procedure. Dwarflab is working on a newer version of their app and I'm curious to see what improvements they will make to the astrophotography mode. Now let's dive into the results. In this time-lapse video, I've compiled individual photos taken by the Dwarf II of the Andromeda Galaxy. What's evident here is that even though the target stays within the telelens's field of view, the tracking isn't flawless. So it's advisable to limit your photo exposure time to around 10 seconds with the Dwarf II telescope to prevent blurry images. Also, despite creating a dark library, I noticed some hot and cold pixels in red, green and blue in the unedited photos. This being said, I did like the final pictures. Here's the unedited stacked picture of the Andromeda Galaxy taken with the Dwarf II telescope. You can see that the tracking wasn't perfect, but you can easily crop the picture a bit to select the area where all the photos sufficiently overlap. Here's an enhanced version after I worked on it in PixInsight and Photoshop. Given that this is a stacked picture created from 10-second photos, I'm quite pleased with the outcome. The Andromeda Galaxy, along with its 2 neighboring dwarf galaxies designated as M32 and M110, are clearly visible. For deep sky astrophotography, the Seestar S50 app has a dedicated stargazing mode. Additionally, the app offers a section highlighting tonight's best targets and a virtual sky atlas for searching various deep sky objects. You have the option to either choose an object and press Go Gazing, or use the virtual sky atlas to zoom in on a specific object, with the red rectangle serving as a preview of the telescope's view, and press Go To. In both modes, after selecting Go Gazing or Go To, the Seestar S50 will automatically move to the selected object in the night sky. It excels at locating deep sky objects with its plate solving technique and rarely disappoints. Once the object is found, the telescope starts tracking the object and enters an automated image enhancing mode for about 2 minutes. After that, the Seestar S50 automatically starts taking 10-second pictures of the object. Similar to solar and lunar mode, you can use autofocus or adjust the brightness using the icons on the right. However, the default mode often produces sharp and high quality pictures without the need to make additional adjustments. When capturing a deep sky object, you'll see a stacked view of the target. At this point, you can log out, switch to your home Wi-Fi and return to the Wi-Fi signal of the Seestar S50 later. The telescope will continue to automatically capture photos of the deep sky object. I found the Seestar app, at least at this point in time, to be much more user-friendly and straightforward for capturing deep sky objects as compared to the Dwarflab app. Let's check out the pictures. First up, this is an unedited stacked image of the Andromeda Galaxy in FITS format from the Seestar S50's memory card. The overlap of the stacked pictures turned out quite well. Also, I didn't see many hot and cold pixels, which was nice. Here's an edited picture of the Andromeda Galaxy's core, taken with the Seestar S50 after post-processing it in PixInsight and Photoshop. To be frank, I was a bit disappointed. While the core of the Andromeda Galaxy looks quite impressive, the Galaxy didn't fit within the camera's field of view. The Seestar S50 has a narrower field of view than the Dwarf II, and its sensor is in portrait mode instead of landscape. Consequently, the camera's sensor couldn't capture the entire galaxy in one frame. I also used both telescopes to capture a 1-hour stacked image of the Eastern Veil Nebula. This nebula is a fascinating cloud of hot, ionized gas and dust located in the Cygnus constellation, approximately 1500 light-years away from Earth. The Eastern Veil Nebula belongs to a supernova remnant from a star that exploded around 7,000 years ago. This nebula appears roughly 3 times smaller in the telescope's field of view as compared to the Andromeda Galaxy. Given that it's an emission nebula, optimal imaging of the Eastern Veil Nebula requires specific astrophotography filters. The Seestar S50 comes equipped with an internal ZWO dual-band light pollution filter, which is specifically designed for capturing emission nebulae like the Eastern Veil Nebula. I wanted to make a fair comparison between the Seestar S50 and the Dwarf II, so I placed a similar ZWO dual-band filter in front of the Dwarf II telelens to capture this nebula. The 1.25-inch filter is available for about $100 or euros. The standard ultra-high contrast filter included in the Deluxe package of the Dwarf II telescope doesn't perform well for this purpose. It tends to block the light emitted by ionized hot gas from nebulae like the Eastern Veil Nebula. Now let me share a 1-hour time-lapse video featuring the individual pictures captured with the Dwarf II telescope. Over this hour, you'll notice the Veil Nebula changing its position and the object undergoing some rotation. This behavior is characteristic of budget-friendly, though not entirely precise altitude azimuth tracking used by both the Dwarf II and the Seestar S50 telescopes. Achieving perfect tracking for deep sky objects typically requires a higher quality equatorial mount with auto-guiding. However, such mounts and guiding equipment come with a much higher price tag as compared to these more affordable telescopes. For more information on reliable equatorial mounts for telescopes, feel free to check out my website at astroforumspace.com. Using both telescopes, I took 10-second photos for an hour and processed the stacked images in PixInsight and Photoshop. Now let me show you the unprocessed and processed pictures from both telescopes. With the Dwarf II, we get a broader field of view of the night sky. However, the Veil Nebula is approximately 3 times smaller than the Andromeda Galaxy, making it appear quite small in the Dwarf II's field of view. Upon zooming in, you'll notice that the resolution isn't optimal, and the landscape view during this capture wasn't favorable. On the other hand, the Eastern Veil Nebula did fit nicely within the narrower field of view of the Seestar S50. During the capture, the Veil Nebula was perfectly aligned with the portrait sensor of the Seestar, resulting in a much higher resolution image of the same nebula. Additionally, the apochromatic triplet telescope of the Seestar S50 produced a cleaner picture as compared to the telelens of the Dwarf II. Before I share my final thoughts, there are a couple of additional points I want to highlight. First off, neither of these telescopes is ideal for capturing planets. It's a common misconception, but despite being closer to Earth, planets appear much smaller in the night sky as compared to the deep sky objects I just showed you. For instance, take a look at this Dwarf II view of Venus in the morning sky. It appears quite small. Similarly, here's a view of Jupiter using the Seestar S50. If it's planetary observation and imaging you want, you'll need a different telescope with a longer focal length and a larger aperture. Check out my website for more information about planetary imaging or join my channel for $2.99 a month and you'll get access to a 3-hour course divided into 6 lectures where I explain how to observe and capture the planets with a backyard telescope. Additionally, both telescopes can be used for capturing daytime photos and videos as well. For example, here are some MP4 videos of birds captured with the Dwarf II telescope. Let's move on to my final verdict for both telescopes. Both telescopes are great options to kickstart your journey into astronomy and astrophotography without breaking the bank. Let's talk about the Dwarf II's advantages first. It's an all-round smart device and its telephoto lens offers a nice view of the night sky, perfect for capturing truly astronomical space objects like the Andromeda Galaxy. Plus, it doubles as a versatile tool for daytime video and photography. You can easily control the Dwarf II through your smartphone using the Dwarflab app. The combination of the wide field and telephoto lenses make it a breeze to frame objects in the Dwarf II's telephoto lens. However, there are also a couple of drawbacks. The Astro mode in the Dwarflab app can be a bit tricky to navigate and the telephoto lens tends to introduce some noise in the pictures. This noise can be corrected through post-processing, but that requires being familiar with astrophotography processing tools and techniques. The resolution of 3 arcseconds per pixel allows for wider field astrophotography, but keep in mind that it might not deliver the highest resolution images. Also, the ultra-high contrast filter isn't great, and I ended up buying an extra duo band filter to capture distant nebulae in space with the Dwarf II telescope. Overall, the Dwarf II is a neat device at an affordable price, making it an excellent tool to spark your interest in astronomy and astrophotography. As mentioned earlier, Dwarflab is offering my viewers a generous 5% discount. You can find the link in the video description below. The Seestar S50 stands out as a very nice and budget-friendly smart telescope. One of its strengths is the triplet apochromatic refractor telescope, which provides clear and decent images of the night sky. The Seestar app adds to its appeal with its ease of use and versatility. The default settings in the app to control the telescope and gaze at celestial bodies like the sun, the moon, and deep sky objects are easy to use, making it user-friendly for beginners who want to explore the night sky with their smartphones. It also serves as a great entry point for those interested in astrophotography. Despite being a compact telescope, the Seestar S50 offers a good resolution, allowing you to observe details such as the craters on the moon, the sunspots on the sun's surface, and other features. The built-in duo band filter enhances the ability to capture details of distant nebulae, like the Veil Nebula I showed you. However, there are some drawbacks as well. The narrow field of view in portrait mode may take some getting used to, and larger celestial objects, like the Andromeda Galaxy, do not entirely fit within the Seestar's view. Additionally, the sensor cannot be rotated to better frame deep sky objects. Another limitation is the telescope's restriction to 10-second exposures, preventing the capture of dimmer parts of certain deep sky objects. In conclusion, with the Seestar S50, ZWO has provided an affordable smart telescope for aspiring astronomers to observe the night sky, expand their knowledge, and take their first steps into astrophotography without breaking the bank. Links to reliable astrophotography shops in the USA and Europe can be found in the video description, along with a direct link to purchase the Seestar S50 from ZWO, which may be especially interesting for people in Europe who are looking to buy the telescope at a more affordable price of $499 compared to the 700 to 800 euros asked for in European telescope shops at the time of this video. It's important to note that my testing period for these telescopes was about 3 months, and they are relatively new products on the telescope market. As a result, I can't say much about their durability or reliability at this point. Both telescopes still need to prove themselves in those regards. I hope this video gave you more insight into both smart telescopes. If you're interested in backyard astronomy and astrophotography, please subscribe to the channel. And if you join my channel for $2.99, I have a great 3-hour course on planetary imaging for you, and I'll regularly provide you with high quality space photos you can print out, edit, or use in any other way you see fit. Thanks for watching and see you in the next video. Clear skies!